Hi, Electron John here. Today I want to talk to you about the charging process on either a plug-in hybrid or a full electric vehicle. So if you look at the computer screen, we basically have a J1772 style connector. And even if it was a DC fast charger with a CCS style connector, we would still have the two main ports on the top of this connector. So we got the line 1, line 2, and the equipment ground. That's kind of self-explanatory. That will be the ones that are delivering, in this case, the 220 volts. Now, if it's a level 1 charger, it would only be 110 volts. But the two more important ones that we want to focus our attention on are the proximity detection and the control pilot. So you might be asking yourself, well, you know, I keep hearing about those two circuits, and what are they? The proximity detection, that's basically a resistance. And there's a series of resistors inside the actual onboard charging module on any type of vehicle that actually has the ability to charge a high voltage battery. And depending on how many of those resistors they go through, kind of dictates a lot. So number one, it'll tell you if there's a charger plugged into the car. Number two, it'll tell you, at what rate it's going to charge at, stuff along those lines. The control pilot, that's the one that is constantly monitored. So we heard about the handshake that occurs between a car and an electric vehicle charger. Well, the control pilot is the one that is primarily responsible for that handshake communication, for lack of better terms, between the car and the charger. So stuff along the lines of what type of charger is plugged into it, if there's a charger plugged into it, how much current the battery can accept in the vehicle. Remember, the car is always in control of the charging process. So if the vehicle is charging normally, that's pretty easy for us because we can use our scan tool to diagnose a lot of stuff that's on the vehicle. We can see that handshake and we can compare it to the graphs that we're going to share with you here today. But if the vehicle is not charging, then all that data is not going to be valid on the scan tool. It's not going to be available for us to see. So we might be able to see, steps 1 and step 2, but we wouldn't be able to see all of it. So we're going to talk to you a little bit about that today as well. So you might be asking yourself, well, where does the control pilot originate from? Does it come from the vehicle or does it come from the charger? It actually comes from the charger. And the later half of this video, we're going to show you it's basically a 12 volt signal. Now, as it goes through the resistance values inside the onboard charger, that's going to change, and that's going to be how the vehicle and the actual electric vehicle service equipment, or charger for lack of a better term, actually communicates. So I'm just going to go ahead, I'm going to power up the actual vehicle here, and I'm just going to plug a level 2 charger into the connector on the vehicle. And I've already got the scan tool hooked up. It's already communicated with the car. I hear that the charger's contactor is closed, and we can see that the vehicle is accepting a charge right now. We can see the little flashing green light that's occurring down there. So I went into the vehicle, I selected to go straight into the control modules, and on this particular Chevy Volt here, it's under Hybrid Powertrain Control Module 2. So I'm going to push that button here, and I'm going to select the live data. And I'm going to select data display, and we'll let it communicate with the car, and it should go ahead and allow me to pull up another screen here that says battery charger control module. That's the one that I'm after to see these voltages that we're talking about. And we'll let it establish communications, and here I get a whole big screen of a lot of different types of information. So number one, again, this is all assuming that the vehicle can accept the charge, and it's also assuming that there's no problem with the vehicle or the charger. I can see here the charger input, which is the very top line, is reading 242 volts. So again, this is a level 2 charger, so it's hooked up to a 220 circuit here. So we're seeing that we actually have a charger that's capable of delivering that voltage here. And I can also see the battery charger input. It's at 6.4 amps. Now, this is important, and this is all being determined from the onboard charger based off of the voltage drop that occurs on the control pilot side of the circuit here. So this is being maxed out here at 6.4 amps. Again, remember, the car is always in control of the charging process. And I can see battery charging system operating conditions. It says yes, which means there's no problem with the vehicle. It's allowing this battery inside this Chevy Volt to accept the charge at this point. Now, if it were to say no, that could either be that there's a problem with the vehicle, problem with the charger, or it could even mean that there's a totally full battery inside this vehicle. Now, this battery is not totally fully charged. We'll see that a little bit later on here. So I can go down through here, and I got battery charger inputs 120 volts and 240 volts. If it was a level 1 charger, obviously the 120 volt one would say yes, and the 240 would say no. But since it's a level 2, that's something I would expect to see. It says the battery charging system's okay, the charge port door is open. I can keep scrolling through here. I see the proximity detection circuit is at 1.49 volts. Now again, this is being derived by which resistors it's going through, and that will change throughout the course of the charging process as the car is communicating with the charger. So I can see that, and as I keep going down the line over here, I can go down battery charger power level, AC level 2, correctly identified the type of charger we're using. It says that the battery charging system status is ready. It's passed the charger control module circuit status, and it's also passed the charger enable circuit status. And then at the bottom, you see I have 3 different control pilot signals. So the one is telling me that the speed at which it's charging has a 10% duty cycle, and that's normal for this type of car. We'll see why here in a second. The control pilot voltage, it starts at 12 volts. That's been dropped down all the way to, let's say, roughly 6 volts, 5.9 volts here. And the control pilot period is at 1 milliseconds here. So that's quite a bit of information. And again, we can use this information to help diagnose, or help check, I should say, that the charging circuit's working the way it's supposed to be working. So if we turn our attention back to the computer screen here, we're going to see that we have a little charging circuit diagram here that shows a square wave signal. We're going to see that live here in a second. And I basically have 4 different states. So state A, which is the full 12 volt area there, it's telling me that the EV is not connected. State B, you can see that drops down to approximately 9 volts or so. That's saying the EV is connected, but it's not ready to charge yet. State C tells me the EV is connected, it's ready to charge, or it is charging, and there's no ventilation needed. So ventilation means that the temperature of either the charging equipment or the vehicle got too high, so they would have to slow down the speed at which it's actually charging. And also we can see in state D, it means that the EV is connected, it's ready, and ventilation is required. So it drops the voltage depending on what the current situation happens to be. And since I'm using an Autel charger, I actually have on my cell phone the charging app. And again, this is a great useful tool if there's no problem with the vehicle. So I can go right through, and it basically is just telling me that it's charging right now. I can hit the charging curve button on the app, and I can see that I'm charging about 6 amps, which pretty much matches what we just saw on the scan tool. And it's telling me that the power that it's charging is roughly, I want to say 1.5 or 1.8 kilowatts or so. And I can also pull up the voltage, which would tell me that it's charging at about 242 volts. So this is all great information. And I can even touch the screen one more time, and I can see, I don't have to try to read the graph. I can see all those digital numbers. So this is all great information. assuming that the car is charging. Now let's talk about a couple things that could happen here. The vehicle could actually not charge at all. So if it's not charging at all, you have a question. Is it a problem with the charger or is it a problem with the vehicle? We could also have an issue where the vehicle is trying to charge, and maybe it is charging, but it's charging at an abnormally slow rate. Or it may be charging and then stopping the charge throughout the process. So maybe you get a customer's complaint that comes in that says, hey, I plugged my car in and it didn't charge at all. Or I plugged my car in and I left it plugged in all night long and I woke up this morning and I only got 3 miles, 5 miles of range when I woke up this morning. And it's been charging for 8 hours or so. We could also have some type of connection problem. We've all dealt with those for every area of a vehicle. We could have some extra corrosion, whatever the case happens to be. So before we get involved with exactly how to diagnose this, let's look at some of the other material I have on the computer screen here. And we can see that for 6 amps of current, that should be delivering a 10% duty cycle. Again, we're going to show you this duty cycle here with the scope momentarily. Now we can see that the higher the charger, so the more capable of the charger, and if the vehicle will accept that rate of charge, that duty cycle will change. So if we go all the way down to the bottom for an 80 amp charger, and if the vehicle could accept that type of delivery from the charger, we would expect to see about a 96% duty cycle on the vehicle as we're testing this. So again, it's easy to do with the scan tool if there's no problem with the vehicle. Now, if there's no problem with the vehicle, most flat rate technicians aren't even going to look at that. So unless the vehicle comes in and they say, there's a charging type of complaint, we're going to be focusing all of our diagnostic attention on whatever the complaint happens to be that vehicle is brought to our shop for. So again, if there's not a charging type of complaint, we're not even going to be looking at those data stream PIDs, most likely. So what happens if the vehicle's not charging? Or we could actually have any one of those complaints that we were saying, charging too slow, whatever the case happens to be, or it stops charging throughout the process. This is where it becomes hard for us as a technician, because with the actual J1772 or even a CCS style connector, even a Tesla style connector, we still have a control pilot and a proximity detection circuit. And the way how those circuits are wired, we would have to start performing some testing. So one of the quickest, easiest tests is going to be that with the vehicle charging port, wherever it happens to be on the vehicle, with the other side of that charging port, this is going back on this particular vehicle to the onboard charging module. This charging module could be located underneath a back seat, it could be underneath the hood, it could be underneath the vehicle, could be part of the high voltage battery pack. But we can't get the first resistance value, which should be about 2,700 ohms, unless we disconnect that harness from the onboard charger. So, how hard is it to disconnect it on the different types of vehicles? So if you see on the computer screen right now, here's a little graphic that I got from a website, which basically shows where the onboard charging module happens to be on this particular vehicle. So it's underneath the car. It's pretty much on top of the back section of the high voltage battery, which means I'm going to have to remove all the splash shields and stuff like that. Hopefully I can squeeze my hand in there to get access to that connector to unplug it so that I can do the first resistance test. And that first resistance test would be measuring the resistance value between the proximity detection circuit and the negative side of the service equipment. And that should be about 2,700 ohms of resistance. Now that's the easiest one to go ahead and measure. And it's a pain in the butt, as you can see on this car. It's a pain in the butt on 90% of the electric drive vehicles that actually will allow you to hook up a charger and charge up the battery. So that is assuming that that was going to be where our problem is too. We don't know. We got to start at square one. We got to rule that out. Now the control pilot circuit, you know, there's not an easy place to tap in to actually get these values that we're after. So, you know, we all got the fancy equipment where we can have the little back probing probes and stuff, and we could try to remove this actual charging port, because that's easier to get to than anywhere else. And we could try to back probe it, and hopefully we can make a good enough connection. But again, all that takes time, and time is money in our industry, as we all know. So what can we do to go ahead and rule out if there's a vehicle that comes in and says it won't charge, a lack of charging complaint? Well, I went ahead and I developed a little tool, and it's a two-part series tool. Comes with some instructions, a little quick start guide, little flow chart, 1, 2, 3, 4, 5, 6. And also it'll come with some detailed instructions on the charging circuit. And it'll come with all the information that we talked about, the different types of amperage ratings and speed at which it charges and all that. Inside this kit are two boxes. The first box basically will allow you to test the charger on the vehicle. So what this does is, if we had a vehicle that came in and they said, hey, it's not accepting a charge, we don't know as a technician, is it a charger that's at fault, or is it something on the vehicle? So this will rule out the first option of it being a charger. So what I've got here is I've got the charging port. This is where you'd plug your charger into. And I have a little board that simulates a car and all the circuits on a car. So the proximity and the control pilot circuit. Now it's going to need some voltage to it. So on the side over here is where I would go ahead, unravel the actual cord, and I would just plug this into a 110, and this is basically going to simulate a 12-volt battery in a vehicle. So I would plug that in. Now, before we get too far ahead of ourselves, let's go ahead and let's talk about the actual charger itself. So I'm going to unplug the charger from the vehicle, and here's the charging ports that we were talking about. This is a charging gun. You'll notice that it's got a little snapper on it here. This is part of the proximity detection circuit. So when we plug that in, if we don't have it plugged all the way in and snapped in place, and this was still held in the upward position, well, the vehicle's never going to want to charge, right? So that's one of the resistance values that we're concerned about on the proximity detection. So think of proximity detection as, does the vehicle realize that there's a charger plugged into it? Is it connected properly? And then some of the communication as to what type of charger and stuff like that is all going to be displayed here. Now, I said before that I'd show you that the control pilot circuit is actually coming from the vehicle's charger here. So the charger that's mounted to the wall. So I'm going to take my little back probe, I'm going to stick it inside here, and I'm going to show you that hopefully we should have 12 volts if I can hold this correctly. So on my screen I got 11.89 volts. So this is just coming right from the charger. That's where the original 12 volts is coming from. Now, we don't have to do this test because this box will go ahead and tell us the results that we're after anyways. But I just wanted to show you how the control pilot circuit actually works. Where is the 12 volts coming from? It's not coming from the vehicle, it's coming from the actual box itself. So I'm going to go ahead and plug this cord into the back of my cart over here so I can get some power. And then I'm going to, again, I just want to see if the charger itself is good or not. So I'm going to plug this into my box, and if the charger is good, the proximity circuit light, which is going to be a little green light, should light up. And I'm going to plug this in, and the little green light lit up. So I know the proximity circuit is good. I also heard that the charger's contactor's closed. So I have 3 ports down at the bottom. I can just measure with my voltmeter if I'm actually delivering any kind of voltage to the other terminals here. So I'm going to take my meter, I'm going to turn this and lay it on its back since I'm working kind of with one hand and the charging cord is kind of pulling things down. So I'm going to go to AC volts on my meter. I'm going to put my leads in. So this is line 1. I can see I'm displaying 121.6 volts. So I can take that red lead out and put it in line 2 and I should be, creating the same voltage there. Now we already know that we are because we saw it on the scan tool that it was 240 something volts there. So we know that the charger is not the problem. Now there's other companies out there that make a tool kind of like the first part of this here. That tool is kind of expensive and it's made for electricians. It's not made for technicians because I can simulate ground faults and stuff along those lines. Now, I didn't build those circuits into this first box because as technicians, it's not like the customer is going to ask us to come to their house and rewire their charger for them. Our job is to just determine what the problem is, why the vehicle will not accept a charge. So we only care if the charger is working properly or not. And we just proved out that the charger is working properly. And I'm going to plug this back in again because something just popped in my head as I was going through this. And I'm going to plug my ports back in so we can see that we have our 121 volts. And all I'm going to do is just take the little flapper on the top of this charging gun and I'm just going to depress it. And as I depress it, you can see that my voltage is dropped down to roughly 2.3 volts. I'm no longer charging the vehicle. So something as simple as just this little latch on the charging gun not being secured properly in the charging port would prevent the vehicle from charging. And we just proved that out with this little box there. And while we were doing that, the proximity light went off because it does not know that there's a charger plugged in. So I'm going to show you some graphs which will help explain this in a little bit here. But at this point, I feel we're pretty much done with the voltmeter there. And you might be saying, well, hey, that's really cool. I know that the charger's good, which the charger was usually easy because we had other tools available to us to rule out as it possibly being a problem. So the second part of this kit, I'm just going to put this box 1 underneath the hood, is essentially, it's a little bit more detailed than what I'm about to say, but essentially a breakout box. And what this tool allows us to do is to go in series with that charging port and the actual charger that's mounted to the wall. So I'm going to go ahead and move my meter out of the way and I'm going to plug just this part in. Now I got another charging gun on this side and it's got the same type of latch. So I'll plug this into the vehicle here. I heard the little snap and I've got, this is just a holster to hold that if you don't want to keep it in the box. I've got a charging port on this side and then I've got the line voltages and the ground again, but primarily I got this control pilot jack that I can go ahead and plug tools into to monitor the charging process. So at this point, what I'm going to do is I'm going to go ahead and kind of show you a couple other things that I have on display here for us. And I'm going to pull up first the proximity detection chart. So this is out of a slide from my PC presentation that talks about the proximity circuit. So we can see that if that voltage reading on the proximity is 4.5 volts, that means it's not connected. If the button is depressed, it should be about 3 volts. And if it's connected to the vehicle, it should drop down to about 1.5 volts. Now we saw that on the scan tool when we had this plugged in, But in essence, what we're doing is, on the right-hand side of the screen, we see the circuit for the proximity detection and how it can go through the different resistors there. Now, again, it starts off if nothing was connected, so if that charging port and the cables going back to the onboard charger, which we just saw is kind of buried on this vehicle, if that was disconnected from the onboard charger, we should see a 2700 ohm resistance if we were to measure that circuit. Now, that's kind of difficult to get to, so we can actually use the voltage readings here, and we can assume, based off of Ohm's law, which ones of these resistors it's actually dropping through. Now, I'm going to go ahead and pull up what I feel is a little bit more important one here, which is the actual control pilot slide. And the control pilot slide here shows us that the 1772 pilot circuit is a 1000 hertz waveform. So it's going to be a square wave if everything's working the way it's designed to work. And it's going to have a voltage reading between positive 12 to negative 12 square wave. The duty cycle will change based on what the car can handle and what type of charger I'm hooked up to. So it goes both ways. If I try to take a level 1 charger and charge a Ford F-150 Lightning, you know, the truck obviously could handle a much higher rate of charge than what that level 1 charger can give it. It will charge, but it's going to be extremely slow. By the same token, if I took a level 3 charger and tried to adapt it to hook up to this Chevy Volt, the car's going to say, well, I know you're capable of giving me a lot more. In fact, even this 220 volt charger that I'm using here in this demo is capable of delivering more amperage than what this particular car can accept. So all that's going to change based off of what the car can handle and the type of charger that I'm hooked up to. And we are going to go from 12 volts, which we saw is coming from the charger itself, and then what that 12 volts gets manipulated into by the vehicle's onboard charger is going to help me go ahead and diagnose this circuit here. So I'm going to go ahead and I'm just going to minimize that, and I'm going to pull up a scope screen, and I'm going to put some leads in the control pilot circuit here. So I'm going to go a lead to the control pilot circuit, just like how we have displayed here. I'm going to go ahead and make my scope go active, and I'm just going to plug the charger into the box. Now I got to wait for the charger to recognize, for the vehicle to recognize the charger is plugged in. We can see that we are charging. There's the green light that's coming on the dash, so we know that everything's hooked up. It recognizes the charger plugged in. There's not a problem with this vehicle. Just wanted to show you the diagnostic steps that you'd go through. I've got a voltage pattern going across the screen here, and if I were to freeze this pattern, at the bottom of the screen is where the measurements are located here. And I can see that I've got a 10% duty cycle that's occurring across the screen here. So with the 10% duty cycle, going back to what we said before, that also matches what the scan tool told us, because again, there's not a problem with this particular vehicle. I know that this is charging at approximately 6 amps. So the real key points here is, number one, we'll use each one of the examples that we talked about. Vehicle comes in and it says it's not charging at all. And we have to determine, is it the charger or is it something on the car? Well, we ruled out the possibility of a faulty charger with the first box. So we saw that the charger was good, it's capable of delivering the voltage. Now I could measure line 1 and line 2 voltages again here, and we would still get the same 120 volts. But for sake of keeping the video relatively short, I'm just not going to do that at this point. So I can see on my scope screen that we have approximately, looks to be about 7 volts or so going across the top of the screen there. And At the bottom, I'm going as low as, looks like, let's say -9 volts or so. So at this point, I know that this vehicle is charging. I know that the charger's good. I know by just simply looking at this waveform that the vehicle should have no problem. So if it was a lack of charging type of complaint, I would not see this waveform. Or if the vehicle was charging way too slow, that would go ahead and affect the actual amplitude of this waveform, and it would also amplitude the speed of the waveform. So let's just throw a scenario out there of I've got some extra unwanted resistance in the circuitry, maybe some green corrosion, whatever the case happens to be. That's going to affect the amplitude and the speed. Also, let's go ahead and say that I have a problem with the onboard charger that's affecting it. So a common problem is on a Tesla, the onboard charger has two 50-amp fuses in it. One of those 50-amp fuses blow. So that Tesla vehicle will actually still want to charge, but it's going to be at a snail's pace. I would see that on this waveform. That would help me diagnose it's taking too long to charge. Now, what happens if we have a scenario where we have, the charging process actually starts and stops, right? The customer's not going to bring the car telling you that, but they're going to say, I woke up in the morning, I only got, 3 miles of range, 5 miles of range, 10 miles of range, whatever the scenario happens to be, and it charged all night long. So I'd want to continuously monitor this waveform, and with the scope, I can record that and go back in the buffer. I can see when this thing will actually start to slow down the charging process. Now, it's normal for it to slow down as it gets to a full state of charge. So once it gets to about 80% or so, it will throttle the speed down and the voltage down a little bit here, because we don't want to have an unrealistic surface charge, just like an old-fashioned 12-volt battery. So we start to do a trickle charge type of effect here. So that's normal. But what happens if the battery's nowhere near 80% charged and it's actually turning the charger on and off, or turning the charging circuit on and off? I have a way that I can quickly hook up a scope. I can use a voltmeter, whatever you're accustomed to doing. If you have a scope, I prefer to scope. And I can monitor this the whole time while it's charging. Now, with that being said, we can see all this stuff pretty quick and easily with the scope. I'm going to go back to our little chart here, and I can see with the 10% duty cycle that that's the 6 amps. That car, this particular car, is regulating that. So I'm seeing the communication going back and forth. I don't have to try to go ahead and back probe a connector. I don't have to start unplugging stuff on the vehicle or anything to try to make a connection, because I have, in essence, a breakout box between my charger and the actual vehicle here. As I scroll around and look at some of the other information that's in the actual owner's manual here, I can see when I first plugged the charger in, I didn't capture this live, but I can see how that voltage will drop down. So it's 12 volts when it's first plugged in, and then as soon as the vehicle gives it the thumbs up and says everything's good, communication starts, I'll see that that voltage drops down, and depending on how you got your scope set up, you see a square wave. Now, I've got my time base stretched out a little bit for sake of the video, but I can actually see that that's occurring here. So in essence, what we did is we have a way that we can monitor the communication or the handshake that's occurring between the car and the actual vehicle charger. If for some reason there was a hard fault of some sort, we'd want to diagnose that first. So if I scanned my vehicle and I had a high voltage related trouble code, Chevy volts, I'm giving you another green bullet here in this video, Chevy volts for the high voltage cooling system, the actual coolant temperature sensor fails on it, and that would store that type of related high voltage trouble code. When that fails, it will not accept the charge. It's not going to accept the charge because it has no way of being able to control the temperature of the battery. So if there's any type of high voltage related diagnostic trouble code, you'd want to diagnose that first, which is pretty much common sense. But if there isn't, or maybe you actually repaired everything else, you have a way that you can actually do a quick line spy type of tapping into the actual charging circuit on the vehicle and get to the diagnostic process and hopefully the actual solution to repair the car a lot quicker and faster. If there's ever a severe problem, say the onboard charger's, totally out to lunch, or there's too much resistance or something like that, it's not going to be uncommon for you to see a negative 12 volt reading on that control pilot circuit. You will see at times that when it goes back to 12 volts or 0 volts, that could mean that the vehicle's battery is at this point fully charged. But again, if it was fully charged, I would never be able to see this communication because the onboard charger, when it's talking to the actual charger on the wall, is going to say, I don't need any extra voltage. I'm fully charged at this point. So, but primarily the customer's not bringing you the car because the battery's fully charged. They're bringing you the vehicle because it's not accepting a charge or it's way too slow to charge the actual battery on the vehicle. So in those cases, this is where this will really shine and help you diagnose these type of charging circuits. So again, this is I call it an EV detective kit, kind of proud of it. It has won a Motor Top 20 Tool Award for 2023 here, and it's a huge time saver, helps us diagnose charging circuit related type of problems, and I look forward to seeing you guys in a future training class. Thanks for watching.